Let's start the last topic of our unit now. I'm going to start it off by drawing a picture that should seem pretty familiar to you from Physics 20. We got a hill. We got a car at the top of the hill. Let's say that car is at rest, 0 meters per second. And let's say the hill has a height of 20 meters. We want to find the speed of the car as it rolls down the hill, reaches the bottom of the hill. How fast is it moving? Not a crazy hard question. You might not remember how to do it right now because it's been a year, okay, but it's still a relatively straightforward question. Does anybody remember from Physics 20 how we would do that question? Andy, is your hand up there? Yeah, initial energy equals final energy. That's right. Anytime you've got one of these roller coaster type problems, and you saw them lots last year, including on your final exam, then EI will equal EF. Now, Devin, what kind of energy does this car have at the top of the hill before it rolls down the hill? It's got something. Otherwise, it's not going to roll down the hill, right? If it's got no energy, it has no potential to do anything. Kirsten? It's got potential energy, right? Gravitational potential energy. It's got MGH. Now, it doesn't have kinetic energy because it's not moving. But as long as you have a height, you've got gravitational potential energy. What about the final energy when we reach the bottom of the hill? Gary, what about the final energy when we reach the bottom? It's kinetic, good, because it's moving. No height anymore, so no potential. Just going to be kinetic here. 1 FmBF squared. Is that good? All right. Well, let's take a look at this. Here we got a positively charged plate and a negatively charged plate. And let's introduce, beside that positively charged plate, a positive particle. It's not moving. But it's going to start moving, right? Because it's repelled by the positive plate and it's attracted to the negative plate. We have a gravitational field over here that causes this car to move down to the bottom of the hill. We have an electric field right here that causes this particle to move to the negative plate. The electric field is like the gravitational field. The positive particle is like the car. The car is going down a hill. The charged particle is going across a gap, accelerating across a potential difference. Here's what I want you to do every time you see, whether it's in a diagram like this or just simply a charged particle speeding up. When a charged particle speeds up, I want you to think of it as the car going down the hill. Visualize the car going down the hill. Are you visualizing it? Can you see it right now? Quinn, can you see it? Quinn, what color is the car? Red car. What kind of car is it? 2-door, 4-door? 2-door, okay. Is it pretty new or old? Is it? Okay. So we got a new 2-door red car. Tara, how many people in the car? How many people in the car? Are they young or old? Young. Probably texting then, right? Are they texting? No? Good, good. So we got two young people, two good young people, because they're not texting in the car, in a red car, fairly new car, 2-door, going down this hill. Okay, picture the car going down the hill whenever you have a charged particle speeding up. Visualize the car going down the hill, and then treat it like a problem with a car going down the hill. Treat this problem over here the same as this problem over here. Let's say EI is equal to EF. Hey, car's going down a hill. What kind of energy does this red 2-door car with two people inside that aren't texting, what kind of energy does it have at the top of the hill? Well, it's MGH. What kind does it have at the bottom of the hill? 1 FmBF squared. Now, this isn't going to allow us to solve for the speed of the charged particle at the other side. So what we're going to do here now, after we visualize it as the car going down the hill, is just replace gravitational potential energy with electric potential energy. Electric potential energy is QV because if you remember, electric potential was E over Q. E was therefore equal to QV. That make sense? So it's exactly the same thing, except for one small part. The potential energy that we have at the beginning is a different kind of potential energy. Instead of being gravitational potential energy, MGH, it's electric potential energy, QV. That's it. That's the only difference. If it's not helpful for you to think of it as a car going down the hill, then I guess don't do it. But I don't know about you. Seeing a car going down a hill is is much closer to being in the realm of my experience than a charged particle speeding up. I can't see that. I never have seen a charged particle speed up. It's a lot easier for me to solve a problem if I can see the problem, if I can visualize the problem. And I can see this. I can visualize this. I can't visualize this nearly as well. Let's change it a little bit. Let's give the car an initial speed now. It's 10 meters per second. While we're at it, let's give this charge an initial speed of 10 meters per second. How does that change things over here on the left-hand side? Abby? Yeah, it's got initial kinetic energy in addition to the initial potential. It's still got potential because there's still a height. But now it's got kinetic because it's moving as well. So we're going to say 1/2 mvi squared plus mgh equals 1/2 mvf squared. Over here, we're going to say, well, what kind of energy does it have at the beginning? Remember, we're picturing it as a car going down the hill. What kind of energy does the car have at the beginning? Potential, and as Javi said a minute ago, kinetic. It's exactly the same thing. When the charged particle speeds up, it's exactly the same thing as the car going down a hill, except for mgh is qv instead. That's it. One more change to this. What if I wasn't looking for the speed at the bottom of the hill? What if I was looking for the speed halfway down the hill? And similarly, I'm looking for the speed of this positively charged particle, not on the other plate, but halfway across the other plate. What kind of energy does the car have at the beginning of the problem? What kind does it have at the beginning? Kinetic and potential. Good. Now, what kind does it have when it's halfway down the hill? It's got kinetic and potential. It's got less potential and more kinetic because you've just had a conversion of potential energy to kinetic. But you still have some potential, just not all of it left anymore. What about over here? Well, again, we're picturing it as the car going down the hill. As the car goes down the hill, it starts off with kinetic and potential. When it's halfway down the hill, it's got kinetic and potential. Sorry, we should have put in mgh for this, right? It's got kinetic and potential. But instead of putting in mgh, we're going to put in qv. Right? Exactly the same thing, except wherever you see mgh, it becomes q times v. Right? Quick little question here. What would hi be right here? What would h initial be in this question? Yep, cool. Good. 20 volts. What's hf going to be in this question if we're going halfway down the hill? Mark? 10 volts. Or meters, I should say. 10 meters, 20 meters, and 10 meters. What's VI going to be here? We had a potential difference of 20 volts across this gap. What's VI, the initial potential, going to be? You guys know this. It's not harder than it looks. Okay, it's not a trick question. 20. The initial potential would be 20 volts. What's the final potential going to be if I go halfway across? Instead of going halfway down the hill, Tara, what's the final potential going to be? 10 volts. Right? It's still the same thing, except V is like H instead of, right? Okay? Whenever a charged particle speeds up, think car going down a hill. Think potential energy converted to kinetic energy, like it is in the car going down the hill. Now, one more picture to show you here. This time, the car is at the bottom of the hill. It's got an initial speed of 10 meters per second. It's going up the hill. Forget about how high the hill is. Doesn't really matter right now. Okay, but it's starting to go up the hill. Car doesn't want to go up the hill. Car doesn't want to go against gravity, but it will because it's moving. It's already moving. It's got inertia, right? Doesn't want to stop. We'd solve this the same way, essentially. EI is equal to EF. But this time, at the bottom of the hill, what kind of energy would the car have? What? Good. Got kinetic energy because it's moving at the bottom of the hill. What kind of energy would it have as it reaches the top of the hill? Cool. Potential for sure. And maybe even kinetic. Depends on whether it's still moving or not, right? Okay, we don't really know with the details of this whether it's still moving or not, but let's assume that it is still moving when it reaches the top. Notice in the last one, it was potential to kinetic energy. This is a conversion of what to what? Kinetic to potential energy, right? Well, let's say this time we've got a charged particle between two parallel plates. Let's say the particle is a negative particle with an initial speed of, let's say, 10,000 meters per second. Does that negatively charged particle want to go toward the negative plate? No, it doesn't. It's repelled by it, right? But will it go toward the negative plate? Just the same as the car will go up the hill. Car goes against the gravitational field, and this negative particle will go with the electric field. It'll slow down just like the car slowed down, but it'll still go. Whenever you see a charged particle slowing down, I want you to think of it as a car going up the hill. Right, Parker? When the car goes up the hill, we start off with kinetic energy. We end off with potential energy and maybe some kinetic energy as well. But the potential energy isn't mgh because it's not gravity. The potential energy is QV. So when a charged particle speeds up, automatically think car going down a hill. When a charged particle slows down, automatically think car going up the hill. You got that? Visualize it. I don't care if you're visualizing it to the detail of knowing how many people are in the car or whether it's a 2-door or a 4-door, right, Quinn? I mean, my point there was, like, see it. Okay? See the car going down the hill or up the hill. Yeah, that's going to help us. Yeah. Okay. Good there? Let's do one problem to end the day then. So it's a pith ball. We keep seeing these pith balls now. These pith balls are really, really light things and good for electrostatics experiments because they're so light. Pith is material from the inside of a plant. That's where it comes from. And it's, let's say, really good for doing electrostatics experiments. So that's why we see it often. Pith ball has a mass of 2.4 times 10 to the negative 4 kilograms. Talk about small mass. 2.4 times 10 to the negative 4 kilograms. Has a positive charge of 1.2 times 10 to the minus 8 coulombs. It's initially at rest at location A in the electric field of a larger charge, down here in the diagram. At this location, the charged pith ball has 3 times 10 to the negative 7 joules of potential energy. As it accelerates, position B, it has this much potential energy. We want to find the speed of the pith ball when it reaches position B. Now, there's quite a bit there. But don't make it harder than it has to be. A charged particle is speeding up. Quinn, what are you picturing right now? Car's going down a hill. If a charged particle is speeding up, it's like a car going down a hill. EI is equal to EF. What kind of energy does that car have, Mason, at the top of the hill? Got potential energy. Except we're not going to call it mgh potential. We're going to call it QV potential, right? Still potential energy. Does that car that's at rest have kinetic energy at the top of the hill? James? No, it doesn't. So what about, oh, we're not going all the way down the hill here, are we? Okay, it says it's initially at rest at location A, and then it goes to location B, which is not all the way down the hill. What kind of energy does the car have when it's part way down the hill? Good. It's got potential and kinetic. 1/2 mvf squared plus mgh. Well, no, it's not mgh. It's qv. It's like saying mgh equals 1/2 mv squared plus mgh, but we're subbing qv in for mgh. We're talking about a charge of 1.2 times 10 to the minus 8 coulombs. Multiply that by VI. What's VI? Oh, we don't know it, do we? Do we? That's bad news, right? No, it's actually good news. Because we don't have to multiply those two numbers together. We already have the initial potential energy, right? It's like saying the energy of the car at the top of the hill is 6 joules. We have the initial potential. We don't need to calculate it. We didn't even need to write in this equation because we already have the value. The initial potential energy is 3 times 10 to the minus 7 joules. If you had VI and you wanted to multiply Q by VI, you could do that, but we don't need to here. The mass of the particle is 2.4 times 10 to the minus 4 times VF squared plus QVF. Well, we know the final energy as well. They tell us it's 1.5 times 10 to the minus 8. We don't need to multiply QV because we have the value of QV already. If you do, then multiply. All right, this goes over to this side by subtracting. 3 times 10 to the minus 7 minus 1.5 times 10 to the minus 8. I think that's 2.85 times 10 to the minus 7. Half times 2.4 is 1.2 times 10 to the minus 4. Let's take this over by dividing. 2.375 times 10 to the negative 3. Now we're going to square root that. And when I square root that, it works out to be what? .04. So we're going to say 4.9 times 10 to the minus 2 meters per second. Is that okay? If that's a car going down a hill, you solve that problem like that. You nail it. Guaranteed. All of you. That's a charged particle speeding up. It becomes a little bit harder, it seems, but it doesn't have to be. Picture it as the car going down the hill, and then just sub in QV for MGH. In this case, again, we didn't even need to go that far. We didn't need to because we knew the value of QV already. Okay, your homework, we're not going to give you very much here because you have your assignment due tomorrow. It's questions 1 and 2 on page 571.